Imagine looking up at the night sky. Every tiny pinprick of light, every twinkle is a story of unimaginable time, temperature, and transformation. Long before they shine above us, stars are born in places darker than night itself. These are cold, vast clouds of gas and dust called nebulae. You might know some of them, the Orion Nebula, the pillars of creation. But they are not just pretty pictures. They are stellar nurseries. Inside these massive molecular clouds, gravity slowly gets to work. It's patient, it's quiet, it's relentless. Over thousands, even millions of years, it begins pulling together hydrogen atoms, the most abundant element in the universe and the fuel for all stars. As more atoms clump together, the center grows hotter and pressure builds. It's like squeezing your hands tighter and tighter around a snowball. But the snowball is millions of times larger than Earth and is made of gas. Eventually, something incredible happens. At around 10 million degrees Celsius, hotter than anything you could imagine, nuclear fusion begins. This is the true birth of a star. Hydrogen atoms start fusing into helium, releasing massive amounts of energy. That energy pushes outward, balancing the inward pull of gravity. This delicate balance, called hydrostatic equilibrium, is what allows a star to shine steadily for billions of years. The very first stars, known as population 3 stars, were likely enormous, 100 times the mass of our Sun, and made almost entirely of hydrogen and helium. They formed shortly after the Big Bang and burned out quickly, leaving behind black holes or exploding in massive supernovae. No one has ever seen one, they're long gone, but their deaths created the heavier elements, carbon, oxygen, iron, that would one day become the building blocks of planets' life, even you. Closer to home, our own Sun formed about 4.6 billion years ago from the gravitational collapse of a portion of a molecular cloud. It wasn't alone. Stars often form in clusters like siblings born together, though they may eventually drift apart. And as they form, they often leave behind swirling disks of leftover gas and dust, protoplanetary disks that slowly clump together into planets, moons, and comets. So in a sense, the same starbirth that created the Sun also created Earth. And the Sun, it's just one of about 100 billion stars in our galaxy, the Milky Way, and there are an estimated 2 trillion galaxies in the observable universe. That means for every grain of sand on every beach on Earth, there are potentially more than 10,000 stars in the cosmos. Most of those stars are not like the Sun. In fact, about 75% of stars are smaller and cooler red dwarfs, which can live trillions of years, so long that not a single one has died yet in the history of the universe. Some stars, like blue giants, burn bright and fast, lasting only a few million years before they explode. And while all stars begin in similar ways, their size determines their destiny. Small stars live long and quiet lives. Large stars live fast and die dramatically. But regardless of size, they all begin with the same quiet collapse in a cold, dark nebula, and a spark that ignites a lifetime of light. As we drift deeper into this stellar journey, let's move gently from the birth of stars to how they live, changing slowly over billions of years, shining through cycles of calm and fire. From the world before the long life of a star. Once a star is born, it begins its longest chapter, what astronomers call the main sequence. This is where a star spends about 90% of its life, steadily fusing hydrogen into helium in its core, radiating heat and light into the surrounding cosmos. For our Sun, this phase will last for around 10 billion years. It's like the adult life of a star, mature, balanced, and quietly burning. Different stars live this part differently. Massive stars, those many times the size of our Sun, burn through their fuel much faster. They're like a candle with a huge flame, brilliant and short-lived. Smaller stars, especially red dwarfs, burn their fuel much more slowly. One red dwarf star, known as Proxima Centauri, is the closest star to Earth after the Sun, and it's expected to keep burning for up to 4 trillion years. That's longer than the universe has even existed. As stars age, their internal structure slowly changes. When hydrogen in the core runs low, the balance between pressure and gravity begins to shift. The star doesn't collapse immediately. Instead, it expands, slowly, gracefully, turning into what we call a red giant. Our sun will become a red giant in about 5 billion years. It will swell so much that Mercury and Venus will be consumed and Earth will be scorched. The surface will stretch out more than 100 times its current size, turning the sun into a huge, cool red orb. But even then, it won't explode. That's a different fate reserved for much more massive stars. Inside this red giant, the star begins fusing helium into heavier elements like carbon and oxygen. Each time one fuel source runs out, a new one can begin, if the star is massive enough. A layered structure forms inside, almost like an onion. Hydrogen fuses in outer shells, helium deeper in, and carbon, neon, oxygen, silicon, until it can fuse no more. But here's a fact that might surprise you. No star can fuse iron. Once a star begins to produce iron in its core, it reaches a limit. Iron doesn't release energy when fused, it consumes it. The engine stalls. And when that happens, the most massive stars face their final, violent moment. But more on that later. For now, picture a star in its golden age, like Betelgeuse, a red supergiant nearing the end of its life, glowing dim and red in the constellation Orion. It's massive, unpredictable, and its brightness has been known to suddenly drop, leading astronomers to wonder, is it about to go supernova? Even our sun, humble and steady, goes through changes in brightness. Every 11 years, its magnetic activity peaks and dips, causing sunspots, solar flares, and bursts of charged particles, coronal mass ejections. These storms can affect satellites and even power grids on Earth, and they are all just whispers of what's happening inside. The ongoing battle between gravity and pressure, fuel and fusion. A star's color can also tell you about its temperature and stage of life. Blue stars are the hottest over 30,000 degrees Celsius, while red stars are the coolest around 3,000 degrees. The sun, a yellow dwarf, sits comfortably in the middle at about 5,500 degrees C. But don't let a dwarf fool you. It's still 1.3 million Earths in volume. As stars age, they release stellar winds, streams of charged particles that drift out into space. Over time, this gentle exhaling creates bubbles around the stars, like those seen in nebulae such as the Helix Nebula or the Cat's Eye. These glowing shells are not only beautiful, but they carry ingredients for future star systems. Yes, even as a star lives, it's preparing for what comes next. The dust and gases it releases will one day feed the birth of new stars. So in a way, stars are never truly alone in their journey. Their energy, their matter, and their light ripple outward across time and space. And just as stars are born in clusters, they often age alongside others. In open clusters like the Pleiades, young stars still shine together. In globular clusters, older stars pack tightly in ancient halos around galaxies, sometimes containing hundreds of thousands of stars, each one billions of years old. Their lives unfold on timescales so vast we can barely comprehend them. But just like every life, even the brightest stars must one day reach their end. And so as we float further into this journey, the light begins to fade, and we begin to drift toward the next chapter in a star's life, death. The death of stars. Not all stars die the same way. How a star dies depends almost entirely on one thing, its mass. Let's begin with stars like our sun. Not too big, not too small, just enough mass to glow for billions of years and eventually fade, not in fire but in silence. As the sun ages, it will run out of hydrogen in its core. Fusion slows. Gravity begins to take over, squeezing the star until helium begins to fuse. The outer layers expand. The sun will become a red giant, growing larger than the orbit of Earth. But this phase is temporary. When the helium is used up, the fusion stops entirely. With no more outward pressure, the core collapses under its own weight. The outer layers are gently pushed away, forming a glowing, colorful cloud of gas called a planetary nebula. These aren't planets at all. The name comes from early astronomers who thought they looked like little planets through telescopes. In reality, they're shimmering death masks of dying stars, lasting only 10,000 to 20,000 years before fading. And at the center of that nebula, a white dwarf. A white dwarf is the final core of the star. It doesn't burn fuel. It doesn't shine because of fusion. It glows only because of the heat it still holds. It's about the size of Earth, but with the mass of the sun. That means it's incredibly dense. A single teaspoon of white dwarf material would weigh tons. Eventually, over trillions of years, a white dwarf will cool and dim into something called a black dwarf. But the universe isn't old enough yet for any black dwarfs to exist. Every white dwarf we've ever seen is still glowing. But what about the massive stars? The ones 8 times, 10 times, even 30 times the mass of the sun? Their end is far more dramatic. These stars burn through their fuel quickly, racing from hydrogen to helium to carbon to neon and beyond. In their cores, the fusion continues until it reaches iron, the element that can't be fused to release energy. When iron builds up, the star reaches a limit, and then, in less than a second, the core collapses. The result is a supernova. In that moment, the outer layers of the star are blasted into space in a wave of light and energy so powerful that it can outshine an entire galaxy. In 1054 AD, Chinese astronomers recorded a bright light in the sky, visible even during the day. It was a supernova. Today, we know it as the Crab Nebula, a glowing cloud of gas expanding from the death of that ancient star. And what's left behind? If the remaining core is heavy enough, it collapses into a neutron star. These stars are so dense that a single sugar cube-sized piece would weigh 1 billion tons. Some spin incredibly fast, emitting beams of radiation from their poles. We call these pulsars, and they blink across space like distant cosmic lighthouses. But if the core is even more massive, more than 2 or 3 times the sun's mass, then even neutron degeneracy can't hold back gravity. The core collapses completely. It becomes a black hole, a place where gravity is so strong not even light can escape. Time slows down near it. Space is warped. Matter falls in, never to return. We don't truly know what lies beyond the event horizon, the boundary where escape becomes impossible. But we do know that black holes exist. We've even captured their shadows, like the famous image of the black hole in Galaxy Mate 7. Stars that die in this way do not go quietly. They leave behind echoes, shockwaves that compress nearby clouds of gas, triggering new waves of star formation. In death, they create the next generation. The elements we need for life, carbon in your body, iron in your blood, calcium in your bones, were forged in these dying stars. You are made of star stuff, as Carl Sagan once said. And it's true. Every breath you take, every step you walk is possible because a star died long ago and scattered its elements into the galaxy. And this death is not an end. It's part of a cosmic cycle. The death of one star becomes the beginning of another. What stars leave behind even in death? A star is not finished. Long after the explosion, long after the light fades, what's left behind still shapes the universe in profound ways. The remains of a star, its dust, its debris, its energy drift across space like echoes from a long-lost song. Let's return to a supernova. When a massive star explodes, it sends shockwaves through space. These waves of energy crash into the surrounding gas, compressing it, heating it, stirring it into motion. The result is what we call a supernova remnant. These glowing clouds stretch for light years, with tangled threads of gas lit by radiation and magnetism. One of the most famous remnants is the Veil Nebula, a soft, colorful arc of pinks, blues, and greens floating 2,100 light-years away. Another is the Crab Nebula, still expanding from a supernova seen nearly 1,000 years ago. Inside it spins a pulsar, rotating 30 times per second, beaming light like a heartbeat through time. These remnants aren't just beautiful, they're useful. They contain everything a new solar system might need. Carbon for life, oxygen for breath, iron for blood, silicon for rocks, calcium for bones. Even uranium and gold made only in the chaos of stellar explosions or in neutron star collisions. Yes, some elements are so rare they only exist because of the most extreme events in the universe. Every gold ring, every platinum wire, every rare mineral born in a blast more powerful than words. And then at the very center of some explosions, there remains a darker mystery. A black hole. Black holes are not just star corpses, they are engines of gravity. They warp time, they bend space. And while nothing escapes from within the event horizon, we can still detect their presence by what happens around them. When gas falls into a black hole, it heats up, glowing brightly in X-rays. Some black holes even shoot out enormous jets of particles, beams stretching for thousands of light years. It may seem strange. The same force that swallows light can also light up the universe. And black holes don't just exist alone. At the hearts of most galaxies, including our own Milky Way, is a supermassive black hole, billions of times the mass of the Sun. These giants didn't form from single stars. They likely grew by feeding on matter over billions of years, consuming stars, gas, and even other black holes. The one at the center of our galaxy is called Sagittarius A. It's about 26,000 light years from Earth, hidden behind dust and gas, but we know it's there. We've measured the orbits of stars whipping around it, some moving at millions of kilometers per hour. And here's something to consider. Without that black hole, our galaxy might not exist in its current shape. Yes, even in destruction, black holes bring order. The gravity of supermassive black holes can help regulate star formation across the galaxy. They help galaxies evolve, helping shape the spiral arms and central bulges that we see in countless telescopic images. In 2015, scientists detected these waves for the first time using LIGO, confirming a century-old prediction by Einstein. It was the sound of two black holes merging over 1 billion light years away. Think about that. The death of stars not only creates new life, it creates ripples in the fabric of reality itself. And still, there's more. The dust from dead stars can drift for millions of years before settling into the birth of new stars. Around these newborn stars, planets form. Maybe some of them are like Earth, maybe some of them carry life. But every single one begins the same way, with the remains of a star that came before. So as we move deeper into this cosmic cycle, it becomes clear nothing is wasted. Not light, not gravity, not even death. Everything becomes part of something else. Stars and the stuff of life in the quiet that follows a star's death. Something miraculous begins. The dust and gas released into the galaxy, soaked in heavy elements forged by nuclear fusion, don't vanish. They drift, they float, they collect in new clouds. In these clouds, chemistry begins again. But now, it's not just hydrogen and helium. Now we have carbon, nitrogen, oxygen, iron, sulfur, phosphorus, the very elements that make life possible. The earliest stars could only produce basic elements, but with every generation, stars added to the chemical richness of the universe. The stars born today carry far more metals than the first ones. Astronomers even classify stars by this. Metal-rich stars like our sun are considered younger. Metal-poor stars, those born in the early universe, are older, more primitive, and it's this growing chemical complexity that eventually allowed for something more. Planets, water, DNA, consciousness. Let's follow the trail. When a new star forms, a disk of leftover material swirls around it. Over time, small particles collide, clump, and form planetesimals. These grow into protoplanets. Some stay rocky, like Mercury, Venus, Earth, and Mars. Others collect gas, like Jupiter and Saturn. But what truly matters is what's in that dust. Without carbon, there are no organic molecules. Without oxygen, no water. Without nitrogen, no proteins. Without phosphorus, no ATP, the energy molecule used in every living cell. All of it, every molecule in your body, was once floating in a cloud of gas from a dying star. Consider this. The calcium in your teeth was formed in the core of a red giant. The iron in your blood was born in a supernova explosion. The oxygen you breathe was exhaled by stars like our sun. You are not just made of stars metaphorically. You are made of stars literally. Even the structure of DNA, its double helix of atoms arranged in patterns, relies on carbon bonds and molecular shapes that originated in interstellar chemistry. And interstellar space isn't as empty as it seems. Within dark clouds of gas, astronomers have found amino acids, alcohols, even sugar-like molecules, the building blocks of biology, floating freely in space. Some scientists believe that life on Earth may have received a boost from comets or meteorites, icy leftovers from the solar system's formation that still carry primordial organic compounds. In 2004, NASA's Stardust mission returned samples that contain glycine, an amino acid from a comet. It's possible that the raw ingredients of life didn't just arise here, they were delivered here. And wherever stars shine, there's the potential for life. We now know of over 5,600 confirmed exoplanets orbiting distant stars. Some lie in what's called the habitable zone, not too hot, not too cold, just right for liquid water. And every year more are found. Some planets orbit red dwarfs, others sun-like stars. Some are massive gas giants, others rocky and Earth-sized. But all of them have one thing in common. They exist because of stars. Even the seasons on Earth, the tides, the photosynthesis in plants, all are driven by the light of the sun, which itself is fueled by the ancient nuclear fire that began nearly 5 billion years ago. Stars are more than distant points of light. They are furnaces of transformation. They take the simplest elements and build complexity. They drive evolution, not just of galaxies, but of matter itself. And the beauty is, it never stops. Somewhere right now a star is being born. Somewhere else a star is dying. And in between, countless planets orbit, warmed by starlight, cooled by nightfall, waiting, perhaps, for life to rise. The cosmos is not a silent, cold emptiness. It is a living story, a chemical garden, a place where starlight becomes oceans, where gravity becomes biology, where death becomes birth again. Stars shape the universe. Step back for a moment. Zoom out, way out, beyond the depth of individual stars, beyond clusters and clouds, beyond the solar systems and nebulae. We begin to see the larger pattern, a web, a structure made not only of galaxies, but the stars that shape them. Stars are not just points of light. They are the architects of galaxies. Every galaxy you've ever seen, those distant spirals and glowing blobs, owes its form, its glow, and even its gravity to the collective lives of its stars. Let's begin with something simple, light. The stars in a galaxy emit the light we use to observe it. Without stars, a galaxy would be invisible. It would be just cold gas and dark matter. Stars illuminate the cosmic canvas, allowing astronomers to trace the shapes, histories, and distances of galaxies across billions of light years. Some galaxies glow with the soft red light of old dying stars. Others blaze with bright blue, evidence of massive stars being born in real time. These starburst galaxies are like cosmic nurseries, where thousands of stars form every year. But stars don't just light the galaxy, they shape its motion. As stars orbit the galactic center, their combined gravity helps define the spiral arms, bars, and halos we observe. The Milky Way rotates like a slow whirlpool, each star pulled by the mass of its neighbors and by the mysterious presence of dark matter. Dark matter doesn't emit light, but it exerts gravity. We only know it exists because of the way stars move faster than they should, given the visible mass. Stars, in a way, are our clues to what we cannot see. And as stars age and die, they release energy back into the galaxy. This feedback from supernovae, stellar winds, and radiation heats the surrounding gas, preventing it from collapsing too quickly. This balancing act helps control the rate of star formation. Too much, and galaxies burn out. Some galaxies form elliptical shapes, smooth and old with little star formation. Others become spirals with sweeping arms, rich in young stars. And some galaxies collide, forming vast tangled systems where new stars ignite by the billions in the chaos of gravitational dance. Yes, galaxies collide, and they often merge. The Milky Way itself is on a slow, graceful collision course with our neighbor Andromeda. In about 4 billion years, the two galaxies will meet, not with crashing planets, but with stars weaving past each other like rivers of fire. The skies of Earth, if Earth still exists, will glow with streaks of stars arcing across the horizon. And over time, the two will merge into one larger, more rounded galaxy. And at the center of each one, again, a supermassive black hole. Remember, these black holes may seem like destroyers, but they help regulate a galaxy's energy. When matter falls in, it creates quasars, incredibly bright objects that outshine entire galaxies. Quasars can stop new stars from forming or trigger bursts of new growth by compressing gas. They are the heartbeat of galaxies, pulsing with energy. Even beyond individual galaxies, stars influence the cosmic web, a vast network of filaments stretching across the universe. Made of galaxies, dark matter, and gas, stars light these filaments. Supernovae send shockwaves down them. Supernovae send shockwaves down them. Their light lets us see where the threads are and where the voids lie. The structure of the universe, its balance between empty space and luminous matter, owes much to what stars have done, and the universe continues to expand. As galaxies drift apart due to dark energy, the light from stars stretches into longer wavelengths, eventually slipping beyond visibility. One day, far in the future, new civilizations may look up and see only their own galaxy, unaware of the vast sea that once surrounded them. But we know that stars form the galaxies. We know that galaxies shaped the universe. And we know that from the tiniest hydrogen atom to the grandest spiral, it was the life and death of stars that made it all possible. And now, as we drift through this thought, imagine what happens next, not in space, but in time. The future of stars and the universe time moves slowly in space, so slowly, in fact, that what we call the future of stars stretches over billions and even trillions of years, and yet even stars must run out of time. The stars you see today, those brilliant steady lights overhead, are just a brief moment in a much longer story. A golden age where light is still abundant, where galaxies shine, where matter still burns. But this age will not last forever. Let's begin with our own sun. In about 5 billion years, it will exhaust its nuclear fuel, expand into a red giant, and eventually leave behind a white dwarf cooling ever so slowly in the dark. It will no longer shine. It will no longer warm planets. It will simply fade. But the sun is just one among countless others. Over the next 100 billion years, most stars like it will do the same. Galaxies will grow dimmer. Star formation will slow. The gas needed to make new stars will run out, either consumed or blown away. Still, some stars will live on. Red dwarfs, the smallest and most efficient, can live for trillions of years. In fact, none have died yet. They burn slowly, gently, with just enough heat to shine dimly through unimaginable time. These stars will outlast almost everything else, but even they eventually will flicker and die. In the deep future, far beyond anything we can truly comprehend, the universe will enter what scientists call the degenerate era. Star formation will cease. The remaining white dwarfs, neutron stars, and black holes will drift in darkness. By this time, the universe will be unrecognizable. Galaxies will have merged or dispersed. The stars will have all gone out. Black holes will rule the night, quietly swallowing the last bits of matter. And still, time will go on. Eventually, even black holes begin to fade. According to Stephen Hawking's theory of Hawking radiation, black holes slowly evaporate over time. The larger they are, the longer they live. But in the end, even they disappear. A black hole with the mass of our sun might take 10 years to evaporate. That's a 1 with 67 zeros. A time so long that the human mind cannot truly grasp it. But in this vision, even the universe's most extreme objects do not last forever. And so the final chapter begins, with no stars, no light, no matter, just a thin, cold fog of particles drifting through ever-expanding space. The universe becomes cold and dark. No more energy can be extracted. No more life can form. This is the state known as heat death or the big freeze. Not an explosion, not a collapse, just stillness. A silence that stretches on until even the last particle decays. But there are other theories too. Some physicists believe in the Big Crunch, where gravity pulls the universe back into a single point. Others imagine a big rip where dark energy eventually tears apart even atoms themselves. And then there's the idea of a cyclic universe, one that ends and begins again. A cosmic heartbeat pulsing through eternity. We don't know for sure. We may never know. But what we do know is this: every atom in your body, every star in the sky, every galaxy spinning in silence is part of this incredible unfolding story, from the first flicker of light to the last breath of time. And you are alive now, briefly, brightly, inside the golden age of stars, the age when galaxies still dance, when light still travels, when stars still burn. The light we see when you look up at the stars, you're looking into the past. Every single point of light above you is a message from long ago, a silent traveler that has crossed oceans of time to reach your eyes. Light doesn't move instantly. It takes time, and space is vast. The light from the moon takes just over a second to reach Earth. The light from the sun takes about 8 minutes. But the light from Sirius, the brightest star in our night sky, it's over 8 years old. The light from Betelgeuse, that giant red star in Orion, more than 600 years old. That means when you gaze at Betelgeuse, you're seeing it as it was in the Middle Ages, before telescopes, before electricity, before printing presses. If Betelgeuse exploded today, it wouldn't know until the 2600s. Zion. And then there are stars so far away, their light has traveled millions, even billions of years to reach us. Some of the faintest specks in the night sky left their home galaxies when dinosaurs still walked Earth. Some left before Earth even existed. The James Webb Space Telescope, launched in 2021, is now capturing the light of the first galaxies ever formed, over 13 billion years ago, just a few 100 million years after the Big Bang. It's the closest we've ever come to seeing the universe's own childhood. And yet even this starlight has been stretched by time. As the universe expands, it pulls light along with it, turning visible light into infrared, a process called redshift. The farther away a galaxy is, the redder its light becomes. Eventually, the most ancient light becomes invisible to the human eye, slipping silently into wavelengths our bodies cannot detect. Still, we try. We build telescopes, satellites, detectors, and algorithms, all to catch these final whispers of the past. Because every photon that arrives is a piece of the story, a glimpse into something larger than ourselves. And still, even in all our searching, we only see a fraction, a thin slice. A thin slice, the observable universe, the part we can measure, is about 93 billion light years across, but it's likely far larger, possibly infinite. And in all that, the stars are just tiny flames, brief bursts in an ocean of dark. But to us, they are everything. They guide ships, mark seasons, shape calendars, inspire poems, paint myths. For thousands of years, humans have looked up and seen patterns in the sky: Orion the hunter, Cassiopeia the queen, Leo the lion, Scorpius the stinger. Entire cultures wrap their stories around the stars, and those stories still shine. Even as science grew and myths faded, the magic remained. Because in truth, the stars are not just scientific objects. They are symbols of wonder, of possibility, of time, of distance, of home. And while stars may seem eternal, they remind us of life's true nature: bright, brief, beautiful. You are made of their light, shaped by their gravity, breathing their chemistry. You live in their orbit, you sleep beneath their glow. And when you gaze up at night, you don't just see stars, you see history, you see fate. You see the universe not as a cold void, but as a memory still reaching you. Starlight in the human soul, somewhere in the quiet before sleep fully arrives. Your thoughts may return to the stars, not as objects, not as data, but as something more. Because even long before we knew what stars truly were, we felt their pull. We stood on mountaintops. We built stone circles. We mapped the sky by firelight. Our ancestors followed stars across deserts, oceans, and generations. We named them. We worshiped them. We told stories to explain why they moved, why they disappeared, and why they came back. Stars became symbols of gods, of fate, of time. They were wishes. They were guides. Even today, when we know they are burning spheres of hydrogen billions of miles away, we still feel something ancient stir when we look up. There's a kind of silence in the stars that speaks louder than any voice. It tells us you're part of something greater. And that feeling isn't wrong, because everything you are, your hands, your heartbeat, your breath, was forged in a star. You are not separate from the cosmos. You are a way for the universe to know itself, as Carl Sagan once said. Think of that. You, lying quietly now, listening gently with eyes closed and thoughts floating, you are made of dust that once glowed. You are the product of countless stellar lives, of supernova long gone, of atoms that traveled across light years to become you. Your body contains trillions of cells, each filled with carbon, nitrogen, oxygen, built from stardust. Your brain carries electric signals made possible by elements forged in ancient cores. Your breath contains air that has passed through lungs and leaves and oceans and clouds, and long ago, through stars. Even your thoughts now, drifting between memory and sleep, are shaped by patterns of light, heat, and time. And just as we are made from stars, we continue to be moved by them. In poetry, in music, in art. Van Gogh painted them swirling above sleepy towns. Chopin set them to nocturnes. Philosophers wondered if each soul was a star waiting to fall, and children still wish on them, whispering dreams into the night. No other natural object blends science and spirit like the stars. They are both real and imagined, both data points and metaphors, both cosmic and intimate. They ask nothing. They just shine. And in their quiet shining, they remind us that time is long, space is deep, and life, however fleeting, is extraordinary. Every star that dies gives life to something else. Every star that shines is a chapter of the universe still being written. And every human heart beating softly in the dark is part of that story. So tonight, as you rest, know that the stars are not far. They are in you, around you, before you, and beyond. A universe inside you. Now we arrive at the end. Not the end of stars, not the end of space, but the quiet, closing moment of reflection where facts become feelings and knowledge becomes rest. You've traveled far tonight, from cold, dark nebulae where stars are born to brilliant lifetimes of fusion and fire, from the final breath of red giants and the roar of supernovae to black holes waiting in silence. You've drifted through the chemistry of life, the shaping of galaxies, the far future of time, and the story of starlight finding its way to your eyes. But here's the most beautiful part. None of it is separate from you. You are not outside the universe watching it unfold. You are within it, made from it, breathing it in, thinking it through. When you lie down at night and close your eyes, you are returning to it. The iron in your blood once formed in a dying star. The calcium in your bones once drifted through a nebula. The light in your mind made possible by atoms that burned in stars billions of years ago. And as you rest, you're not falling away. You're falling into something greater, into the flow of time that connects all things, into the quiet rhythm of the universe, still expanding, still glowing, still becoming. Maybe the stars are not just lights in the sky. Maybe they are memories, fossils of time, quietly burning so that we may remember where we came from. Maybe the stars are reminders that even in darkness there is brilliance, that even after death there is creation, that even in silence there is story. And maybe, just maybe, the universe is not out there at all. Maybe it's within you, folded into every breath, every heartbeat, every quiet moment before sleep. So now, let go. Let the stars take over. Let your thoughts slow, like the cooling glow of a white dwarf. Let your breath rise and fall, like waves of starlight across an ancient sky. You are stardust. You are gravity and light. You are a whisper of the cosmos. And tonight you are at peace.